So today we're going to dive into one of the most powerful and frankly coolest ideas in all of mathematics and engineering, the Fourier series. It's a concept that, once you get it, reveals these hidden patterns that are literally all around us, in everything from the sounds we hear to the tech we use every single day. So let's start with a puzzle. What could a quiet snow tire, a perfectly tuned engine, and a single musical note possibly have in common? I mean, on the face of it, they seem totally unrelated, right? One's about stopping noise, one's about making power, and the other is about making sound. But as you're about to see, they're all connected by the exact same, really profound mathematical idea. And the answer to that puzzle? It's the Fourier series. Now, I want you to think of it less like some scary, complex formula and more like a universal recipe. It's a method for taking apart and then rebuilding almost any repeating pattern you can possibly imagine. The core idea is, honestly, it's surprisingly simple. Every good recipe needs ingredients, right? Well, for the Fourier series, the only ingredients you'll ever need are simple, smooth waves, sines and cosines. That's it. By just adding them together in the right amounts, you can build pretty much any repeating pattern, even something with sharp corners like a square wave. Let's actually see how that works. Okay, so imagine our goal is to create a sharp, blocky square wave. We're going to start with our very first ingredient, just a single, pure sine wave. Now, it's not a great match yet, is it? It's too smooth, too rounded. But this is our foundation. This is where it all begins. All right, now let's add our second ingredient, another sine wave, but this one's a little different. It's got a higher frequency and it's smaller. And just watch what happens. The second we add it in, the top of our original wave starts to flatten out and the sides get just a little bit steeper. You can see it's already starting to look more like the square shape we're aiming for. And this, right here, is the core of the whole recipe. We just keep adding more of these simple waves, each one with its own specific frequency and size. And with every new ingredient we mix in, our approximation gets better and better, getting closer and closer to that perfect square. So the big takeaway here is that a complex wave isn't really a single thing at all. It's more like a chorus of simple waves, all combined in perfect harmony. So that's cool, but how do we find the exact recipe for any shape we want without just, guessing? Well, this is where the mathematicians came up with some really incredible shortcuts that make the whole process, well, pretty elegant and super efficient. So the first big shortcut is all about symmetry. If the pattern you're trying to build is perfectly symmetric around that vertical y-axis, we call that an even function, then your recipe is only going to contain cosine waves. And if it's symmetric around the origin, an odd function, then you're only going to need sine waves. This is huge because it immediately cuts our potential ingredient list right in half. The second, and honestly the most powerful shortcut, is this property called orthogonality. Yeah, it's a bit of a mouthful, I know, but all it really means is that each one of our sine and cosine ingredients are fundamentally unique. They don't interfere with each other. And this independence is the absolute key. It lets us isolate each ingredient inside the complex wave, almost like using a prism to split white light into a rainbow, so we can measure the exact amount we need for our recipe. No guesswork involved. Okay, so we've got our recipe book. Now, let's go back and see how it's actually used to build real-world solutions and solve that puzzle we started with. So remember that noisy snow tire? The early designs had these treads that were all evenly spaced. As the tire rolled, this created a perfect repeating pattern that produced this incredibly loud and annoying whine at one specific frequency. That's a dominant harmonic. Well, using Fourier analysis, engineers could literally see this loud spike in the frequency data. Their solution was brilliant. They just randomized the spacing of the treads. This didn't get rid of the sound, but it spread all that acoustic energy out across a bunch of different frequencies, turning that awful whine into a much, much quieter hum. And the engine, well, every time an intake valve opens and closes, it creates these periodic pressure waves inside the intake pipe. So what engineers can do is represent these waves with a Fourier series. And by carefully tuning the length of that pipe, they can make its natural resonant frequency line up perfectly with one of the powerful harmonics from that intake wave. This resonance literally helps push more air and fuel into the cylinder. It's called inertial supercharging, a performance boost with no extra mechanical parts. How cool is that? And this same recipe-based thinking is absolutely critical in physics. So imagine you only have data for half of a system, like the temperature along one half of a metal rod.
Fourier's method lets you intelligently complete the picture. If you know the ends of the rod are insulated, you create a symmetric, even extension, which builds your model using only cosine waves. If the ends are fixed in place, like a guitar string, you create an odd extension using only sine waves. It's all about picking the right family of ingredients to perfectly match the physical reality of the problem you're trying to solve.
But for all of its incredible power, the Fourier series isn't quite perfect. Nope, it has this strange, kind of unavoidable little quirk. You could almost call it a ghost that lives inside the math.
And this ghost, it always shows up and it's always the same size, about 9%. Now, what on earth could that be? This is what's known as the Gibbs phenomenon. Whenever a Fourier series tries to build a sharp corner or a sudden jump, like in our square wave, it always overshoots the mark by about 9% of how big that jump is. And here's the really wild part. No matter how many sine and cosine waves you throw into your recipe, that 9% overshoot never goes away. The little ripples get squeezed closer and closer to the edge, but the peak of that first overshoot, it always stays. It's a fundamental limit of trying to build sharp edges out of perfectly smooth waves. So when you step back and you put all of this together, the Fourier series becomes way more than just a tool for math. It's a completely new lens for viewing the world. So what's the big takeaway here? Well, it's that what we perceive as a single complex signal, the noise from a tire, a pressure wave in an engine, a musical note, is really a chorus of simple, pure frequencies all singing together. The Fourier series gives us the recipe. It lets us deconstruct those signals, filter out the parts we don't want, and amplify the parts we do. And even its flaws, like that little 9% ghost, teach us something really profound about the fundamental nature of waves. So the next time you hear a musical note or feel the rumble of an engine, remember the recipe. Ask yourself, what simple waves had to come together to create this complex reality that I'm experiencing? And what hidden harmonies are shaping the world all around you? Thanks for digging into this explainer with me.